Hello everyone, this is Ketish here. In this video, I'm going to go through the AQA Physics Paper 1 Higher Tier from 2018. Question number 6 is on the topic of atomic structure, mainly to do with the uses of nuclear radiation. Smoke alarms contain an alpha radiation source and a radiation detector. Figure 9 shows part of the inside of a smoke alarm. So you have a plastic casing on the outside. This is what we would actually see. And a small opening at the bottom, which is where the smoke particles should go through. Radiation detector on one side connected to the alarm circuit, and the alpha radiation source on the other. The smoke alarm stays off while the alpha radiation reaches the detector. Why does the alarm switch on when smoke particles enter the plastic casing? So if the radiation is going from the source to the alarm, that means it's switched off. As the particles actually move in between the source and the detector, it would be absorbed by the smoke particles will actually absorb the alpha radiation, and that means there is no more radiation coming into the detector that would trigger it off. So you could say the smoke particles stops or absorbs the alpha radiation. Question 6.2. Why is it safe to use an alpha source radiation in a house? Now, alpha has the lowest range, so it's not going to come down into the to the ground level. Smoke alarms are fitted at the ceiling, so it's only a couple of centimeters, less than 10 centimeters. That's the range. And because it's also in a plastic casing, it's not going to come off of the plastic casing. It's actually pointed sideways, so it's not pointing downwards, right? And even if it does, then the penetration power is far less, so it's not going to go into your body because it'll be stopped by our skin or by our clothing. So any of those will be fine. Alpha radiation is not very penetrating, so it does not penetrate the skin, and you could say it does not travel very far in the air. Any of those 3 points will give you a mark. Next question. The smoke alarm would not work with a radiation source that emits beta or gamma radiation. Explain why. Well, beta and gamma radiation are more penetrative than alpha. So beta being less penetrative than gamma, it would go through paper. So it would naturally go through the smoke particles, or it might not be absorbed as much as the alpha particle. Beta and gamma radiation will penetrate smoke, so there won't be a change in the count rate. That would be detected. Or you could say beta and gamma radiation will not be stopped by the smoke, and the change detected in the count rate will be far too small. Next question. Figure 10 shows how the count rate detected from the radiation source in the smoke alarm changes with time. So you have a graph showing the count rate in seconds on the x-axis and the time in half-lives. So time in half-lives, that's interesting because that's first half-life, second half-life, third, fourth, fifth, and sixth. So it's not in seconds or in hours or years. So before I move on to the question, just want to point out, you don't see a lot of questions where you are seeing time in half-lives. At 0 half-life, you're talking about 100% radiation. After 1 half-life, that radiation level is going to go to 50%. Remember, it decreases by 50% every single time. So by the second half-life, the radiation source is going to be 25%, then 12.5%, 6.25%, 3.125, and so on. So it's important to understand if the radiation source that we are using, after if it goes over 2 half-lives, then it's weak. The radiation source is actually weaker because there's only about 25% or less than that. The question: the smoke alarm switches on when the count rate falls to 80 counts per second. Now 80 counts per second is over here, right? And that's about, see if I can get that line straight. So 80 counts per second. Let's draw that line again. So that, there, and then it should, yeah. So there you go. Explain why the radiation source inside the smoke alarm should have a long half-life. The reason it should have a long half-life is even if it goes past about 1.3 half-lives, then the radiation level is going to go past 80 counts per second, which means the alarm will be triggered all the time. There isn't enough radiation going into the detector. For that reason, it should have a long half-life. So a long half-life means the count rate is approximately constant or at a steady level. Or you could say a short half-life means the count rate decreases quickly. So after 1.3 half-lives, the smoke alarm will be activated all the time. Or you could say until 1.3 half-lives, the count rate is above the threshold for the smoke alarm to be activated. Or until 1.3 half-lives, the count rate is above 80 counts per second. I think these 2 bullet points will give you the 2 marks. Next question. Figure 11 shows a patient who has been injected with a radioactive source for medical diagnosis. So you have a radiation detector on the top. Explain the ideal properties of a radioactive source for use in medical diagnosis. Now, the ideal source should have a couple of properties. One, we can't actually use alpha because it's a short range. So you can see the distance is much larger. You could use maybe beta or gamma. And alpha will not go through the skin. Beta will, and so will gamma. Now, beta compared to gamma is more ionizing, which means it could actually cause damage to our cells. So beta is not the best compared to gamma. Gamma is more powerful, so it is more penetrating, but it is less ionizing than beta. So for 4 marks, could say, okay, the source should have a short half-life, right, for a couple of hours maybe. That way, when the patient is exposed to it, or when it's inside the body, they're not going to be radioactive for a very long time. So the patient can be discharged within a couple of hours. And it should have a low ionizing power. That would mean it would cause less damage to the cells, tissues, or the organs or to the body. And it should be highly penetrating, like gamma radiation, so that it can be detected outside the body. That brings us to the end of question number 6. I will see you in question number 7.